Signal Processing Lab course for spring 2014. This is the schedule for the second half of the semester. We're currently right now on the lecture for April 2nd, which is going to start on match filtering. This is really more about pulse amplitude modulation. Match filtering is a big part of that in the receiver design. And we'll go on and finish out the next few lectures in communication systems, and we'll move on to quantization, data conversion, and review in midterm 2. And like midterm 1, midterm 2, I will post solutions online. So let's move on to match filtering lecture 14. Not on YouTube. It's on media site. All right, so here's lecture 14, match filtering and digital pulse amplitude modulation. A lot of topics in here. This is a 4-part lecture. A lot of stuff to cover. So the first part, here it's listed as a 2-part lecture, which is true, but then each part has 2 parts. All right, so our outline here, we're going to talk about today transmitting 1 bit at a time. From a transmitter to receiver, we'll do 2 bits and look at what happens as well. Next lecture, next part 2 will be match filtering, pulse amplitude modulation system. Part 3 will be communication performance. Part 4 will be intersymbol interference and eye diagram. Let's go on to do the first part of lecture 14. Now, this is something we've seen before. It's okay to see it a second time. Now, if we transmit 1 bit, ultimately what we want to do is convert a piece of digital discrete time information to an analog continuous time waveform for transmission over a medium or propagation through a medium. The medium is going to be a physical world. It's going to be continuous time, analog and amplitude. So our transmission on communication channels will be analog and continuous time. One way to transmit the digital information, we've seen this before, is 2-level digital pulse amplitude modulation. We've seen this many times. So we have one way to, again, convert a 0 bit to a continuous time analog representation. We can use a rectangular pulse. The rectangular pulse is a duration capital T sub B. B here is the bit duration. The amplitude for bit of value 0 for this encoding is negative, but we could have done it the other way. But for here, we have the amplitude to be non-positive, I suppose, to be complete. There are values of which it's 0. So it's 0 over here, and it's 0 over here. For a bit of value 1, we're going to send a pulse shape. And again, we've chosen rectangular pulse for convenience, easy to work with. And this pulse shape will have a non-negative amplitude for the bit duration, capital T sub B. Pretty simple on the transmit side. Now on the receiver side, it has some work to do. So this transmitted waveform, this rectangular pulse, goes through some medium, and here we're just modeling the noise of the medium. So you can close the back door if you wish. So the additive noise, so this is just a very simple model of the channel. We're just going to model additive noise in the channel, and really when we do this as a model in the channel, we're really including we're summing all of the independent noise sources that's in the system. It not only includes the channel, it may also include some analog front-end effects. So it's just an aggregate or conglomeration of all these independent noise sources. And so what's a good Cisco model for this additive noise? So it's at least thermal noise, lots of it. And what are the independent noise sources in thermal noise? What's moving around? Electrons, right? So lots of electrons moving around. And we're assuming that they're moving independently of each other. And we can come up with a model for all of this thermal noise out there. And so what's the distribution would be? Statistical distribution? Gaussian, right. So so you can think of it lots of ways. So think about it as a power spectrum. In theory, it's got flat power spectrum. In terms of its amplitude statistics in the time domain as an additive signal. So we can model the additive noise in the channel as a signal. We can call it W of t. This is spectrally flat Gaussian noise. So each amplitude value for any point in time little t, W of t takes on a value that's random. That random value follows a Gaussian distribution. That Gaussian distribution, for our purposes, will have zero mean and variance sigma squared. And sigma squared also represents the noise power. Okay, so we can also, we'll talk about this next part of this lecture 14, so in part 2. But as a preview, if we looked at now, if we were able to compute the spectral content of this spectrally flat Gaussian noise, the name kind of gives it away. Okay, so the power spectrum, that is to say the power of the noise at any particular frequency, is constant. Okay, this is a model, and like any model, it has its limitations. Right? So now, why can we say it's Gaussian? What do we know from probability statistics that we can? Central limit theorem, right? We talked about this last time. So the central limit theorem says if I add a bunch of independent random variables, the distribution of that additive combination converges to a Gaussian as a number of variables heads to infinity that I'm adding together. No, so this is all a nice mathematical model. It's an approximation. Actual noise isn't Gaussian exactly. Power spectrum are not exactly flat. This is a nice model, and it's really modeling the case. If I could sit back and observe the noise for all time from minus infinity to infinity, which I don't have the luxury to do in practice, but in theory I can do this, then the power spectrum is this perfectly flat entity in the frequency domain. This is power spectrum. This is in the magnitudes, absolute value. This is the power spectrum, power at each frequency location. What this tells us is that the noise is equally present at all frequencies, in theory. And it's a model. And so in practice, it's going to vary from this. And we'll look at some cases a little bit later. All right, but for now, I'm only modeling the additive noise in the channel, nothing else. We'll have a filter here for frequency-dependent distortion. The receiver now is going to receive the transmitted waveform plus, really, at any point in time, the additive noise. And that means for any point in time, I'm going to add a random number to the transmitted waveform. That's all I'm doing here. It's a simple channel model. So I've given you a hand drawing of what that might look like here on the right. This isn't an actual simulation, just hand sketch. So I might see something that looks like this over the bit duration. I'm assuming, as you might guess from looking at this, that the receiver is synchronized to the time of the transmitter. We'll talk about how that happens at another time, and that's not easy. All right, but for now, it's synchronized, so we know when we're starting to receive. We know when message data comes at us. And so in practice, we can use a header of PN values and correlate and find the start of a header sequence, and then after the header, we know the data will come at us. There are lots of ways we can synchronize. All right, so we assume we've synchronized, and now all I really see at the receiver is just the transmitted waveform plus this noise, and nothing more. And I've asked you this before, so how does the receiver decide which bit was sent? What would you do? Take the average. Why not? And then do what? See if it's positive or negative. That's it. Okay, so pretty simple for the 2PAM case. So all the receiver has to do, so what I need to do on the receiver side, I'm going to average over one symbol time, or one bit duration in this case. I'm going to integrate whatever comes in over each bit duration, and then I'm going to compare against 0. And I'm going to get back a bit estimate. That's now there's a lot behind this. This is just the additive noise, and I'm assuming synchronization. There's a lot of idealisms here. Go ahead.
The process you just described, is that done like with analog hardware?
Yeah, right now all I've done here is I'm completely so far showing you the analog continuous time story, right? But ultimately, we can do this lots of ways. I could put an analog to digital converter on the receiver and then apply a filter, FIR filter, over the symbol duration. It's a finite length filter. So really this integration is only over the symbol time, and then I restart the integration over the next symbol time. So really this integration is over a finite period. It's just an averaging filter. And really to make it and I've left out the averaging part of this. Let me add that back in. We don't need it here because we're comparing against 0. Let me go ahead and add it in for completeness. It's really an averaging case. So I really have 1 over TB, T sub B here, in the receiver. Right? So I'm averaging over, so I'm integrating to get the total area, and I'm dividing by the amount of time to get the average value. Okay. Now, since I'm only comparing against 0 after the integration, I really don't need, this constant of 1 over T sub V isn't going to change the comparison result. I can not worry about that. But for, 4-level PAM, now it starts to get more interesting because now I have 3 levels of comparison for 4-level PAM, and I have to include now this constant. But for just 2 PAM, or also known as binary phase shift keying or BPSK, I just have to compare against 0. So I don't need this 1 over T sub B. I don't need this constant here. Okay, so again, I can do this in discrete time, and we will in lab. We'll do it in homework. You've actually done it a little bit already when you did homework 4. I'm going to have a filter operation in the receiver, and that filter will run over the symbol time. And go ahead.
So this is a symbol period or a bit period?
In this case, it's 1 bit per symbol, and so 1 bit period is the same as 1 symbol period.
Okay, so
right.
How do you average over 1 bit?
Well, again, this averaging is happening in continuous time, so I'm averaging over this time interval from 0 to T sub B, whatever I receive. Okay, so this averaging, now it's true, this is an averaging operation. I'm going to get 1 value that comes out of this averaging operation. So I have 1 value that comes out per symbol time, and really what it is, it's an estimate of the amplitude. So it's an estimate of the symbol amplitude for the nth symbol. I'm just doing 1 bit here, so it's, we'll do 2 bits in a second, but. So really I want to repeat this over and over again, every symbol period, or in this case every bit period, get the average value over that interval. I assume that that's my estimate of whether or not I was positive or negative. But really what it is, it's an estimate of the symbol amplitude. Because what is this value going to be equal to? Well, this is going to be really what happens over the symbol time. This value is going to be minus capital A plus the noise. So if I average over the symbol time, what I've really done is I've smoothed out the noise. I've averaged out the noise to get a better estimate of the amplitude. In this case, minus capital A if I send a bit of 0 at the receiver. I'm low-pass filtering. Right? We looked at the integrator before in homework. It has a low-pass. If we do it right, if we're careful, we can make it a low-pass filter. And here we're being careful because I'm only integrating over a finite amount of time. I can't have the output grow without bound. I don't have to worry about bibo stability because I'm using this integrator over a finite length of time. So I'm really using it as an FIR filter. The impulse response is finite in length and duration, and not the usual continuous output of the integrator, which you just saw in homework. So in this case, we're using it in a way that makes it bibo stable. because we're only applying the integration over a finite period of time and then restarting the integration with the next symbol time. Okay, so if I send a bit of value 0, I get, this transmission of minus capital A and amplitude over the bit duration. And in the receiver side, I receive, minus capital A plus random noise over that symbol time. And again, the averaging this out helps us smooth out the noise, helps us reduce the high frequency noise. Smooths out the noise, gives us a better estimate of A. Okay. And then all I'm going to do is take the average value. So I'm going to get an estimate very close to minus capital A. And now in this case, all I really need to do is compare against 0. So my estimate can be fairly wrong in estimating minus capital A. I can be off by a lot and still get the detection right. If I send a bit of value 1, I send a pulse of capital A and amplitude, and I see something very similar on the receive side. I see capital A plus this additive noise over the symbol period. Again, averaging this out gives us a good estimate of the symbol amplitude, in this case capital A, but all we really need to do is compare against 0. Now I'm going to make a mistake some of the time. This won't be perfect detection. It's possible. So when am I going to make a mistake? If the average value has the wrong sign. And so when could that happen? That's right. The spike of the noise is large enough to bring the average to the wrong sign. That's right. So another way to look at that is, if the noise power, and that noise power is sigma squared. So more noise power, the more likely I am to make a mistake. And this is intuitive, the higher the noise power, the lower the signal to noise ratio, because the signal power is staying the same, provided the capital A is the same value that I use in different trials. Then if the noise power increases, the signal to noise ratio will decrease, and I have a higher chance of making a mistake. We'll quantify that in part 3 of this lecture. Okay, but intuitively, if my noise is stronger, I'll have a more likely chance of making a mistake in the receiver as to what bit was transmitted. Now it turns out this integrate over the symbol time, we'll show a little bit later in part 2, probably in part 2, it's the end of part 2, that this is the best we can do. This is the best filter we could do for this pulse shape. It turned out to be the match filter, although it's not obvious right now, but we'll look at this a little bit later. This is the match, this integrate over the symbol period is the match filter for the pulse shape of a rectangular pulse. It's the best thing we can do. And by best here we mean it maximizes the signal to noise ratio after this averaging operation is done, which is to, really what it is average over the symbol time and just take one value. It's just one value coming out of that for the symbol time. So it's the best thing we can do in terms of the signal to noise ratio at the estimate here, A sub n hat, or A hat of n, I guess. Okay, we'll show this in part 2. Oh, I do. So this integration is really another way of filtering with an FIR filter whose impulse response is a rectangular pulse. So if you know the pulse shape using the transmitter, the match filter impulse response will be very much related to that. And we'll see what that is. It'll be a flipped and scaled version of the pulse shape used in the transmitter. It's coming up in part 2. Go ahead.
Would this be kind of the best filter to use when you're trying to filter signals that just are just a DC component with just noise added onto it, an integrator like this?
Yeah, this is again, if you integrate over a finite period of time, you're fine. Right? Remember, the integrator has trouble if you let it run over an infinite amount of time and you have a DC input, your output grows without bound. But over a finite period of time, yeah, this is a good way to estimate the DC value over.
If you're measuring over kind of just.
Because what is it? I mean, what is this? This is really a DC value, right? That's a DC value over the symbol period. So it's also on midterm I asked about DC offset in communication systems, and so that's a way to estimate what that DC offset is. All right, now let's do 2PAM, but this time the channel model has memory and no noise. Okay, so we have two-level digital pulse sampling modulation over a channel that has memory. That memory is represented by an FIR filter, so it's a linear time invariant system for my communication channel. And we've talked about why this model makes sense in lecture 12. So this model has finite impulse response, lasting capital T sub h seconds. I use the same encoding as the previous slide for my 2PAM. If I send a bit of value 0, I send x naught of 0 over the channel, and the result is a convolution of the two signals here, the transmitted signal and the impulse response of the FIR filter for the channel model. And we get a trapezoid, and I've asked you about how to go about detecting what bit was sent here, and you've told me in the past a couple things. One is we can still average over the symbol time, or I can just sample at the right location in the valley here. All right, so two ways to go about it. I don't have noise, so the sampling works pretty well. But really, with noise, what I want to do is average over the symbol duration. Now, there's a little issue here, as you might imagine, is that there is a transient, or not transient, there is a group delay effect here. There's an amount of time that the channel needs to fully respond to the input. Now, that group delay, given the symmetry of the impulse response, is what? What's the group delay here? Half TH, right? Because of the symmetry and the impulse response, it's even symmetric about the midpoint. That even symmetry means that the group delay is a constant, and that group delay is half the TH here. So the group delay ends right about here. The worst case delay is capital T sub h for this channel. For this channel model, I should say. All right. So I have to figure out some interval. If I'm going to average over the symbol time, or the bit time, I have to figure out when to start. Right. So I could be safe and start at T sub h and integrate through T sub h plus T sub b. That's one symbol duration. So throw out the first so many seconds of received data and then start integrating. So I could throw out T sub h or half T sub h. Either one's fine. For the sending a bit value 1, very similar story because we don't have any noise in this channel model. Either I can sample the peak, the plateau here of the trapezoid, or again I can take the area over one symbol time and decide whether that's positive or negative to decide what bit value was transmitted. What happens if I do the area and I get 0? Okay, let me translate. You don't know what to do, okay? So what do? Guess. That's a fine choice. So we don't, if the average value over the symbol duration is 0, I don't have any, good way to determine. Assuming that the probability of sending to 0 is the same as the probability of sending to 1, then I really don't know. I can flip a coin, pick a bit. Or just always choose 0. So you can always force the comparison instead of being, is it greater than 0 or less than 0? You can bias that comparison and say greater than or equal to 0 or less than or equal to 0 to bias that case of 0 one way or the other. Go ahead.
When taking the RMS of the signal, the viable option is like an Alice system. And how the sinusoid has 0 average, right?
Mm-hmm.
The RMS of the signal.
So what would you get if so in the case of getting all 0, you get it basically for if I had a receive signal as best I can draw it, let me get enough. All right, so there's one. I've done my best that the average is 0 by hand drawing. I'm sure I missed a little bit. But let's say I have enough. It looked a little bit too sinusoidal. All right, let's just say that the average value is 0 there, just for sake of argument. So you're saying take the absolute value squared and take the, with the root.
Square it basically, and then we take the average.
But see, the problem is that once you take the square of anything, you're going to have a hard time distinguishing minus capital A from capital A.
Oh.
Yeah, that's the problem. So if this were to sum, if this receive signal y of t were to sum to 0 or have an average value of 0, then again we can either bias it either to 0 or 1, or we can flip a coin to generate the answer. And as you might imagine from an implementation point of view, it's a whole lot easier to bias one way or the other. You know, avoid the having to generate a random number. Okay, let's talk about 2 bits. Back to back. And we certainly want to do this. We don't want to send this 1 bit. That wouldn't be a very interesting system in many cases. And we're done and we never send another bit. I mean, I suppose there might be some applications. But for, we'd like to send a lot of bits, not just 1. And we also like to send them in a way that's efficient use of the resources we have in the communication system. Either we have time and we have frequency to use. All right, so let's go ahead and transmit 2 bits. And we're going to see if they interfere with each other at the receiver. So I'm going to transmit 2 bits or pulses back to back, and this will cause overlap, or what's known as intersymbol interference at the receiver. So here I send a bit of value 1 and a bit of value 0 back to back. And so I send the 1 and I send a 0, and I don't wait. I just send it. If I look at the convolution of this transmitted waveform with again, we're assuming a channel model that's just memory, no noise. There's no additive noise here, so as in the previous slide. So I see what's familiar. I get the bit of value 1 is this rectangular pulse convolves with the rectangular pulse of the channel impulse response, and I get what's in blue. The second bit convolves, and you see it spreads out in time. So it's no longer T sub B in width, it's TH plus T sub B in width due to convolution. The bit of value 0 also goes through the channel, and it comes out wider than before, same width, so it's T sub H plus T sub B. And you'll notice I have an overlap. So there's a region in the time domain in the receive signal, shown here in the purple dash ellipse, that I have intersymbol interference. This is reality in communication systems, like reality, like when we sample, we always have aliasing. In a communication system, in practice, we'll always have some amount of intersymbol interference. And the question is, as a designer, how much do we need to reduce, and how do we reduce it? So that's going to be an issue, because clearly if I start applying the match filtering idea or averaging over the symbol duration, and I pick from T sub H, and I pick from T sub H for my symbol period to T of H plus TB, T sub B, then I'm going to pick up contributions from the other pulse that was transmitted. So I'm going to get a different answer. And if I add some noise to this, I'm more likely to make a mistake. So the intersymbol interference causes additional, or generally causes additional errors in the receiver. So how do we do with that in practice? So again, if I were to, so I have a couple ways to decode this. One is I can sample at what I hope is the plateau, either in the peak or the valley, or I can average, over one symbol duration. And anyway, so again, the sampling here idea to try to hit, you know, the peak or the valley is fine when there's no noise. But in practice, we're going to have noise. So in practice, we're going to filter over the symbol period, and we're going to get contributions due to intersymbol interference and trying to decide what bit was sent. So the question here is, how do we prevent this intersymbol interference, or really in practice reduce? In theory, prevent, but in practice reduce the intersymbol interference at the receiver. Okay? Got some thoughts?
To go back to sampling would get messed up by noise just because there's a chance that there could be a spike
Oh, yeah.
to the other side.
Yeah, when you're taking just one sample,
Right there.
that's right, when you're taking just one sample in the symbol period and you're basing your whole decision of what bit was sent on that one sample, it's really easy to get corrupted by noise. So it's a much better estimate to average over the symbol time and then use that to decide what bit was sent. So I will give you a hint. One answer is filtering, and one answer is to do something else. Okay, go ahead.
Would one way to reduce this interference would be like slow down, like make it space out a bit?
Yeah, space out. So one solution, and these can be used together, and they are actually in many systems. So one answer is to spread out, put in the guard interval between the first bit and the second bit that I transmit. Now, how much delay would you put in? So, okay, it depends how bad your system is, but from this model, how long would you wait? Capital TH, right? So if you wait, in other words, if you don't transmit for capital T sub H seconds between bit transmissions, then what you allow is this convolution effect to finish before the next symbol arrives at the receiver, or bit in this case, right? Now, what's the drawback with that method? Right, so I increase transmission time, which means I reduce the bit rate. I reduce the amount of bits per second that I can transmit. There's one other issue. I have to know T sub H. Okay, so in practice, so one way to do that is the receive. So how would you do it? How would you estimate T sub H? And I can send that back, and then communicate control channel that's really low rate, very reliable. So I can send back to the control channel the estimate of T sub H. Now, that's one way to do it. In practice, many standards simply set hard code that value and kind of figure out what's the maximum T sub H that they see in the field, and they just make that part of the scan. This happens in DSL, happens in power line communications, some Wi-Fi standards. So it's a pretty common deal. If we need to know this delay.
Professor Evans, I lost your wireless mic.
Uh-oh. Yes, you did. How far back did you lose it?
About 40 seconds.
Oh, great. Okay, we'll go back. Okay, so I asked you what are the two ways to prevent intersymbol interference. So one way was to add a guard interval between the two bits. So if we wanted, what does that mean? It means that if I transmit, I'll transmit and then not transmit. I'll transmit one bit, wait, and then transmit the next bit. And this guard interval will be TsubH seconds. I have to know what that TsubH is, so my choice is I either set that value, hard code it, and again, many standards do. DSL does, Powerline Communications does. There's a lot of standards that do this, that hard code this wait time. In fact, OFDM systems in general have this encoded, Wi-Fi, etc. It's very common. So they have a waiting period called a guard interval, and then we'll send the next bit. Now, in the case of a system like DSL or Powerline, this is actually a symbol. Then there's a guard interval and another symbol in those standards.
I'm kind of confused as to how filtering would help eliminate.
Right. So that's a second solution. Second solution is filtering. Well, this channel is a filter. This channel is distorting the transmitted waveform. The impulse response is a rectangular pulse, and the Fourier transform is a sync, so it's a low-pass filter. So if I could compensate for that low-pass filtering in the receiver, what kind of filter would you use? If I have a low-pass filter in the channel, and I can add a filter at the receiver, so that the cascade of the channel and the receiver filter, which is called an equalizer, is all pass. What's the receiver filter going to look like? High pass. So we can, again, you need some cues from the transmitter. The transmitter has to send PN sequence or something like it over the channel, and the receiver will then train an FIR filter typically to undo this channel distortion. Inverse filter as best it can. Undo the damage, if you will, as best it can. It won't be perfect undoing of the damage or compensation. So those are the next. So those two issues are on the next slide. Worked out. And so again, option one was wait TsubH seconds between pulses and the transmitter. There are other things we can do in this TsubH seconds. So more common. There's other things we could actually transmit something in this waiting period. We don't have to not transmit anything. So in many standards today, Powerline, DSL, Wi-Fi, we actually do transmit something here, but it's not new data. But it has structure to it that lets us, again, compensate for this channel memory between transmitter and receiver. But just for simplicity, we'll call it 0, but in practice, it turns out to be usually something else. Okay, so we have the guard interval away, which is good. It's a good solution. Right. We wait between bits, transmit, and now, in theory, I do not have any intersymbol interference, provided I know exactly TsubH at the transmitter. Disadvantage, we already said, we have to know TsubH, and we lose data rate. It reduces the bits per second we can transmit through the channel. Option 2, use the channel equalizer and the receiver. In practice, we do both. We do both of these things when we can. Now, in some standards, don't use equalizer. Excuse me, it's not a very good. Involve one. But there's usually, even in certain Wi-Fi standards, there's at least some way to compensate for the channel distortion. Even though it's not a separate FIR filter in the receiver, you still have some ways to do that. So in practice, we tend to do something at the transmitter side and something at the receiver side to combat intersymbol interference. It's usually not an either-or in many standards today, two-way communications.
So the transmitter side would be the waiting.
Yeah, it would be this. That's the transmitter side. Right. So it's the option 1 is the transmitter solution. Option 2 is the receiver solution. And option 2 is homework 7. It's coming later. At the end of the semester. All right, so let me put this kind of together in a block diagram. Really, this is a 2-level PAM system. And now we're going to use a more complicated channel model for this. So ultimately, we're going to start with a stream of bits, B sub I. We're going to have a clocking of that bit, which is the bit duration. And in this case, since it's in this example, since it's 2-level PAM, the symbol time is equal to the bit duration. It's just 1 bit per symbol. L is 1, number if I were to sample this stuff. So the symbol, anyway, so the symbol time is equal to the bit duration. I'm going to encode each bit into one of two continuous or analog amplitude values, minus A and plus A, and I can do 0 to minus A and one maps to A. I can do either mapping. It's just the receiver has to know what mapping I'm doing. So I can map TsubI is 0. This maps to AK of minus A, and a bit of value 1 maps to capital A. But again, you could do this the other way as long as the receiver knows. I then pulse shape. So now I have a stream of impulses that come out of this PAM encoding. This PAM encoding step is the lookup table, and it's also the impulse modulator. Both are kind of block. So I come out of this PAM block here with an impulse train, and each impulse has its amplitude scaled by either minus capital A or capital A. I go through pulse shaping. Why do I have pulse shaping?
Signal like the train.
For transmission, so I'm certainly not going to transmit an impulse coming.
Yeah.
Even if I had my impulses as narrow rectangles. And why would I not do that?
I mean, I would have a hard time detecting that.
Detection's a problem. What about other things? Because those rectangle pulses are so short, hard to detect, yes.
Bandwidth would approach very large noise, or even
Bandwidth would be infinite.
Oh, because it's a sync.
It's a sync. Remember, more than that, an impulse train in the time domain is an impulse train in the frequency domain. So it uses up all bandwidth. So, so pulse shape, 2 reasons. It makes detection easier, and it limits the bandwidth that we use. This pulse shaping filter is low pass in frequency selectivity. Channel's going to have memory. And we represent this with an FIR filter. Rectangular impulse response, if you wish. Additive, you can say historically it's called white Gaussian noise, which is fine. I tend to use spectrally flat. Spectrally flat's a little bit more right. So we add this up comes out of the memory block. You put the noise after the filter. If you put the noise before the filter, then we get spectrally shaped noise, which doesn't match thermal noise. So again, this is really more the thermal noise model is this little WT follows the Gaussian distribution, 0 mean, and the variance is this capital N naught over 2. On the receiver side, we'll have a match filter, and its job is to reduce the impact of noise. That is to say, it's going to improve the signal to noise ratio. We'll talk about that derivation in the next part, lecture 14. And we've already seen one way to do this, which is averaging, integrate over the symbol time. So we average over the symbol time. What that really means is that we run an averaging filter, and we take the last value that comes out of that. Another way to say it is, I look at these two operations. This is really average the received signal for one symbol period, one value. So I'm going to take one value per bit duration. Remember, bit duration is the same as symbol duration. I use that one value to decide by comparing it against some threshold whether a bit of value 1 or 0 was sent based on the constellation map that I'm using. So that's the signal path for both the transmitter and receiver to get bits from one place to the other. A lot of things that are not shown here that you have to do with synchronization and so forth. The equalizer isn't shown in this block diagram. It would be one of those. But the basic signal path is here. Encoding, pulse shaping, transmission, propagation through the channel, reception goes through a match filter, sample to the symbol time, and then I decide what bit was most likely to have been transmitted. Now there's a involved formula. If the bits are not equally likely, then the threshold, the more complicated formula is here. I pulled it from a textbook. We're not going to drive this. And we won't even need it after the slide I just showed here for completeness. P naught is the probability of sending a bit of value 0, and P1 is the probability of sending a bit of value 1. if the probabilities are equal, then what happens to the threshold? 0. And we're going to assume, we always assume that they're equally likely for this class. So this is a more general formula. Now, what's not shown in the system is, again, synchronization of the symbol clocks at the transmitter versus at the receiver versus the transmitter. So the receiver has to adapt its symbol clock, both in duration and start time, to match the transmitter symbol clock. That's a whole set of processing that's not shown. Okay, so let me set up the discussion for next part. So if I now zoom into the receiver and I talk about the match filter design, the match filter has a very important job to do. It is going to help the detection of a pulse, and this pulse could be rectangular pulse, truncated sync, truncated race Gaussian. So it's the detection of a known pulse in the presence of additive noise. The good news is that the receiver, we know what pulse shape we're looking for. We know the transmitter is using rectangular pulse, sync, race Gaussian, whatever. And for this derivation, we're going to ignore channel memory. We're assuming that any channel memory, again, which we represented by an FIR filter, is compensated by an equalizer. We're just going to assume that that's taken care of for us. So what we have at the receiver is, so out of the transmitter, I'm going to be sending pulses over the channel. The channel model for this case is simply additive. So white Gaussian noise, respectively flat noise. At the receiver, there's the transmitter, there's the channel, and here's the receiver. So at the receiver, we're going to apply a match filter and sample at the symbol side. The match filter's job, again, is to pass as much of the pulse signal through and as little of the noise through as possible. So if we look at what happens, we've got a lot of LTI system stuff here. So the match filter will assume to be LTI, linear and time invariant, initial conditions are 0, and so forth. So YFT is the convolution of, so YFT has 2 components. The output of the match filter, YFT, has 2 components. First component is GFT times, convolved with H of T. Standard stuff, filters in the time domain. And we have another input, which is the noise. So because it's LTI, we can use the additivity property. So X of T here is G of T plus W of T. So the output Y of T is going to be G of T convolved with H of T plus W of T convolved with H of T. And that means that Y of T has 2 components. It has a component that is related, this G naught of T, to the pulse shape and the impulse response of the match filter. And the second term is the noise. And so what we want to pass is G naught of T. We'd like to have as much power in that as possible. And we'd like to have N of T, which is the filter noise, have its power as low as possible. To derive what the impulse response would look like to get us there. In the next part, I'll tell you what the answer is ahead of time. The derivation is long. The derivation gets us to this answer, H of T. So the best value of H of T that we can have is some gain times the pulse shape, symbol time, minus continuous time, and conjugated. A long derivation for a very simple result. But this tells me for any pulse shape, it's just as an example, here we go. It's a pulse shape, it's a rectangular pulse that lasts for Tsim seconds, length 1. What's the match filter look like in terms of its impulse response? So I flip this in time, flip it, and delay it by T still. The T here is Tsim, sorry. Lots of times running around. So I flip it, delay it by Tsim, flips this in. Except the amplitude is some constant. Okay. And k could be 1. If k is 0, what happens? Nothing gets through. Not a very interesting filter. All right, there it is. All right, we'll see you in Friday. Record this. Hey, Scott. Hey, Scott.
Yes.
Did you lose audio again?
I did, but I got you on the classroom mic.
All right, good. I think it's batteries. I think it's batteries. No, actually, I don't know what's going on.
It's like we're getting power samples from ISO our embedded system. And no, so what we're trying to do is we're trying to use and right now in our lab is there like a specialized type of filter for the powering out DC, or should we just try to